The objective of this lab was to construct a mass spring dampener mechanical system and, using a second electrical system, record feedback from the mass spring dampener system and generate data points to develop a Bode plot and determine what type of filter the mass spring dampener was acting as. The analogous qualities of both systems, the electrical and mechanical, also allowed us to develop a transfer function.
In our theory, we will discuss about how we can compare mechanical and electrical systems, explain the mass spring damper system, how the mechanical system acts as a filter, and talk more about the dampening in the mass spring dampener. Comparing mechanical systems to electrical systems. The mass spring dampener we were working with is analogous to an RCL circuit. Analogous electrical and mechanical systems have differential equations of the same form. The analogous quantities can be seen on this graph here. The mass spring damper's equations are of a force voltage system. From this graph, you can see the spring acts as a capacitor, mass acts as an inductor, and the dampener acts as resistance. Why? The spring stores energy when the motor rotates. It gives kinetic energy into the spring that is then released. The mass acts as an inductor because when the mass's velocity is going one way and the spring is going another way, it takes energy to move the mass back. The dampener acts as resistance. It is the loss in velocity in the system. With the system being analogous, this allows us to get a transfer function, just like we do from an RLC circuit. These are the transfer functions which are derived in our results. How the mass spring dampener acts as a filter. Just like an RLC circuit acts as a filter, with the mass spring dampener giving the same second-order equations, it does too. The mechanical system can have the same type of passes and attenuate signals. With given data points found in our results, we can plot a Bode plot to determine the type of filter this system is and describe its characteristics. Now let's go back to talking about dampening. On an oscillating system such as the spring, damping reduces the oscillation. This happens by dissipating energy that is stored in the system. In our case, the energy it takes to move a mass that is going the opposite direction with a given velocity. There are 4 types of dampening in any system, mechanical and electrical. They are overdamping, critical damping, underdamping, and undamping. Overdamp returns the system to equilibrium by exponential decay. Critical damping returns quickly as possible without an oscillation. Underdamping is when the system oscillates with the amplitude gradually decreasing to 0. And undamping, of course, the system keeps oscillating at a resonant frequency. You can determine the type of damping from the transfer function. What is resonant frequency? This is a frequency at which amplitudes is at its maximum. This produces large oscillations. This occurs in systems that store and transfer energy. This is known as a cutoff frequency, which soon after an increase or decrease will occur on a Bode plot. The equation for resonant frequency is the square root of the spring constant over the mass.
When creating a system, it is important to know what is required. For our system, user input, output, and the use of the mass spring system are things we need to make our plan work. We narrowed it down to make a frequency, send it to the system, get data, and then plot the data. Using a microprocessor, we created a sine wave and used a code along the lines of if the voltage is positive, then move the motor forward, and if the voltage is negative, go reverse. With a reverse and forward signal and using an H-bridge, we can turn the motor clockwise and counterclockwise. The system shown is a replica of the one we use. The encoder is a clear cutout pattern that is shown. The output can be compared to the distance of the encoder as it is turned, the speed being the slope. To catch this, we use infrared LEDs along with the phototransistors to catch the patterns across the decoder. Catching the two outputs, we get a wave equivalent to the one shown. To make capturing the wave easier, we set up an op-amp comparator that catches the tip of the waves to get a square wave. We adjust this so they are about 90 phase shift apart. After voltage dividers going into our second microprocessor, our program captures the waves and decides if the output goes up or down. The project as a whole works by taking in user input, that is a frequency, encodes it into an H-bridge signal that can be used by the motor to spin the mass spring dampener. We capture that signal with the LEDs and phototransistors. We use a comparator to set it to a square wave, and we use the decoder from a second microprocessor to move the wave up and down, giving us a frequency out.
We derived the analogous differential equation of the mechanical system from the electrical counterpart. Our results indicate that the system is a low-pass filter with bandpass characteristics. Our frequency sweep ranged from 0.01 Hz to 1 Hz. This range of frequencies best depict the characteristics of the system. At 0.2 Hz, the system shows bandpass characteristics because the system allows a frequency to pass through again. The system maintains this until around 0.6 Hz, then frequencies begin to be attenuated again. A few data points were outliers, but overall the data created an apparent trend.
Okay, to conclude, as you could see from our results section, the mass spring dampener acted as a low-pass filter with bandpass characteristics. However, despite our conclusions, we did have some difficulty, and there's some things we would have changed. The biggest problem in the mechanical system was the decoder. We had a decoder to start. However, later we switched to a decoder that had more spacing between each row of spacers, I guess. And we found that gave us much better results on the oscilloscope. And another issue was the LEDs and how they had to be implemented to be right on top of each other and completely vertical was very difficult, considering the size, the relatively small size of the mass spring dampener and the size of the decoder. We think a much bigger, obviously a much more large scale decoder and mass spring dampener would make it a lot easier for us to see changes and move stuff around if we had issues. But overall, it was still doable. Sometimes the spring itself also would move side to side, and that would affect our results because then the LEDs would no longer be positioned at the proper spots on the decoder. Another thing is that the decoder itself wouldn't be held upright by a bolt a nut, because the nut actually, when you increase the frequency of which the mass was rotating, the spring was rotating, the nut would oscillate up and down and would come into contact with our circuit components, and that was not good. It was skewing our results, so we had to change it to some form of putty to hold the decoder up, but at times that proved not strong enough when we increased the frequency. So just little things like that if you had this experiment on a larger scale, I think you wouldn't have as much problem because you'd have more components, bigger, more spaced out. Just space, I would say, is the main issue with such a tight area. But overall, we were still able to get some good results, as you could see from our results section. Mr. Metz, Jacob, this one's for you guys. Thanks for all your hard work this semester. Hanging out with us on Friday afternoons, evenings, and nights sometimes. You guys put it all out on the line for us. You're the real MVPs. Stay chill, Mr. Metz.